we just walked through one sort of simple example of the steps in determining an equation of motion. And so to remind you, there's sort of the component of thinking about those steps, determining system boundaries, deciding how you're going to talk about the system, or you can think about it as one particle, multiple particles, rigid bodies, deciding what interactions you're going to include, representing that system boundary and those interactions with a free body diagram, then thinking about how you're actually going to mathematically represent the system by deciding on a coordinate system, deciding on mathematical models, and finally combining all of those ideas along with the sort of idea that force is a flow of momentum to determine what the equations of motion are. So in this video, I thought we would do the same thing, but do it for a slightly more complicated system than we did before. And this is a system that I think if you talk to Zoe, she'll confirm that this was a system that gave them a lot of headaches last semester for their final project. They were thinking about this question of how can we model a person jumping on a pogo stick. Okay, so the sort of idea is you've got a person, and that person is standing on a pogo stick, and they're flying through the air, and at some point the pogo stick hits the ground with the person on it, and the pogo stick compresses, and maybe it rotates in one direction or the other, and then propels the person back off the ground at some other angle. So that's what the sort of nominal idea is for this, and I draw that nominal idea both to sort of show a case of kind of thinking about it, but it might be worth spending a little bit more time thinking about it. So what do we think is actually going to happen when this pogo stick hits the ground? I think if you think about it, there's sort of a rubber stopper down at the bottom of the pogo stick. So it seems to me the one thing that would be reasonable to say is that the actual bottom of the pogo stick probably stays fixed in location with regard to the ground. Another thing that you can see is the actual forces here are going to be sort of funny. The pogo stick is going to be pushing along the axis of the pogo stick. On the other hand, the person center of mass is actually located off of the pogo stick. Pretty clearly, gravity is going to be important, and it also seems like there's sort of two phases of motion, right? There's sort of phase one here when the person is flying through the air, and presumably the person can do all kinds of crazy tricks with the pogo stick during the time they're flying through the air. But then there's a second phase of motion, which is during the time that they're in contact with the ground. Okay, so that's sort of an example of thinking it through. Obviously, I could draw some more detailed keyframes for this, and if I were doing a longer video, I might do that. But I'd like to move on now to thinking about system boundaries a little bit. And in particular, since this is two phases of motion, I'm going to identify at this point that I actually need to build two models. I need a model for the sort of flying, so there's sort of the flight model, and then there's the bounce model. And for each of those phases of motion, I really need to actually go through all the steps. I need to think about how am I going to model the system during this phase? How am I going to think about transitions between this phase? What are the interactions going to be, and so on. So let's just zoom in on the bounce model, and we're just going to think about how to model that phase of motion and not think too much about the flight component. I propose the flight component would probably be quite a bit easier. Okay, so the first thing that we want to think about is system boundaries for this. And it seems pretty clear that we're interested in modeling a person on a pogo stick, right? So there's the person, and there's the stick. And there are a lot of ways that we could think about that system, but we can say immediately outset kind of this is the thing that we're interested in modeling. Maybe we're interested in what goes on inside of this, but certainly we're interested in how this system interacts with the rest of the universe. So we have at least one system boundary, which is between the system and the rest of the universe. Now the next question is, do we want additional system boundaries? Like, do we want to deal with how the actual stick moves and how the person moves? How do we want to think about the person's motion? So this is sort of getting into the second question of how do we frame the system. And I'm going to propose that our initial framing of the system is a really simple one. That we take this whole system and we say this whole system is a point mass. And that point mass is connected to the rest of the universe through some sort of funny forces. So, for example, you might say actually the point mass is located wherever the sort of center of mass of the person plus stick is, but one of the things that it's connected to the rest of the universe through is through some kind of funny spring, which is offset, has this sort of funny offset. So this sort of says that the person's arm keeps the point mass some distance away from the actual pogo stick, but the actual pogo stick exerts a force that's only along the direction of the pogo stick. So this is a reasonable framing, I would claim, from a couple of perspectives. One is that it seems to me that pogo sticks typically weigh a lot less than people. And so to that extent, thinking about the stick as kind of being a massless thing is not unreasonable. And certainly it is the case that the person is going to be rotating as well as translating, but for a first pass model, understanding how the point mass moves is not a bad step to take. All right, so we've got some idea of what the system boundary is. We're framing the system as a single point mass. So now let's think about what the free body diagram looks like for this, what the interactions are and what the free body diagram is. And I'm going to sort of combine those two things together because I think that drawing the free body diagram helps me to think about what the interactions are. So I'll draw the actual person again with the pogo stick. And I need to think about what are the forces that are acting on that person. And this is actually a really interesting question because your first inclination is going to be to say there is a normal force acting at this point. And that would be a great inclination if you were actually modeling how the stick moved. But the stick is actually not, the stick has been abstracted to this point mass, which is connected to the rest of the universe, not via contact with the ground, but instead via a spring that is connected to the ground. So if I actually think about what the forces are, one force that is acting on the system is actually a spring force that is acting along the pogo stick, and that sort of has its origin at the ground, right? So it's the stick pushes down on the ground with a spring force. The ground pushes back up on the stick with an equal and opposite spring force. And then the second force that obviously is going to be important here is that gravity is going to be acting at the person's center of mass. So I have two interactions, gravity and the spring force, and my free body diagram looks something like this. Okay, so at this point, I could start to really think about what the mathematics of this are. And the first step for thinking about the mathematics of it, or now that I've got my sort of system boundaries and I've figured out how I'm going to think about the system identified, I really need to draw an abstraction that allows me to think about a coordinate system and parameters. So let me draw that abstraction. Well, so I've got the point mass, and the point mass is offset from the spring by some distance. So let me call that, I'm going to call this distance L, which represents the sort of length of the person's arm. That sort of tells me how far the person's center of mass is located away from the pogo stick. And then there's also some distance, which I'm going to call D, that is the length of the stick at any given instant, right? And then that stick is actually attached to the ground and is at a pivot on the ground, right? So from a coordinate system perspective, I would say this looks to me like maybe polar would be helpful here. So I could think about the pogo stick as having some angle theta with respect to the ground. That angle theta will tell me what the orientation of the system is, and similarly, if I know what theta is, I know what d is, and I know what L is, I can actually tell you where the person is located at any given time. Pretty clearly, I need to think about what the mass of the person is. That's going to be a parameter that's important. This spring will have some spring constant k and some rest length d naught. And so at this point, I've identified both what the coordinates are and also what the parameters are. So the sort of coordinates that I need are d and theta, and possibly L if I decided the person was able to move their arm back and forth, sort of change the length of their arm by bending their elbows. And the parameters are clearly the mass of the person, the spring constant, the rest length of that spring, and then L could be in either one of these categories depending on how you chose to model the system. Okay, so we have at this point our coordinate system, we have our parameters, we know what the interactions are, and I think we'll stop at this point on this video, and in the next video we'll walk through the mathematics of this.